Okay. Right, so just a brief introduction to our cluster. Our cluster is, this is the team. It's titled Adaptive Structural Skins. We had a very ambitious project here, was to bring a few things together. One was to bring research into digital tools and means with digital fabrication. So, you know, the physical with the digital. The other ambition was for, well, at least for a structural engineer like myself, is to make structures move and to make structures adaptable and responsive to different conditions, as structural engineers normally make buildings and designs which are static. We started off looking at some research work in origami, looking at some work from others, because we learn from others and continue the research. So this is work from Tomohiro Tachi. We sketched out, we sat down, we brought a team together which had Dan Piker at one end, the designer of Kangaroo, who you all know, and Gregory, who put together this great system for folding metal plate and creating foldable structures. We sketched out different ideas of how we could make modules which could connect into continuous skins, so building envelopes that could adapt and create variable structures. And then we thought, how are we going to do this in the context of a very short 4-day workshop? And so we looked at very simple technologies. Of course, we could have gone to, and we will go to all the way to actuators that can move and deploy structures. But we thought, why don't we just use the simple physical properties of, you know, struts like sprung steel? So we can buy a lot of tape and use those struts in their sort of unbuckled condition to carry load, and when they're buckled to fold and allow the structures to fold. Gregory, you want to?
So this is an example of some curved folding, and so what we found actually is that these types of surfaces can be described in the same way as these origami structures that Daniel was just showing us. So they're essentially linkages. So we had these two ways we could describe curved surfaces that could be adapted and changed. And one was with this linkage system that Daniel just showed us, and another with these curved surfaces. So we did quite a lot of sort of manual investigation into these surfaces. How could we describe these? And we found that some of the ways that they were described were getting quite extreme in the sort of the surfaces that we had. But we found that we could simulate these in Kangaroo as well. So both we took the physical properties of these paper models and then simulated those in Kangaroo. And in Kangaroo, we could actually take something that would be quite simplistic and start to change that and twist the surface into something more complex. And our aim there was to try and optimize the structure. So we wanted to then, so what we did is also use the AKT plugins to try and see how can we take a shape like this, which we can easily change into some freeform shape, but optimize beam depth and the particular fold pattern to be more structural. And we came up with this system which basically would take these sort of amorphous shapes, which were very flexible, and then actually stop them moving and freeze frame them really in a way that we find to be their most optimum. So this system here has two of these types of surfaces intersecting. And once they intersect, that flexibility of this sort of hinged linkage system is completely removed and they're sort of locked in position. So here's a little diagram of how that works. So the blue surface is intersecting the red surface, and as it does that, it really becomes an extremely stiff and stable structure. So we used a bit of some of RoboFold's internal software. So this is our CAM software. So if we're making changes to the structure, we could update this. It's all linked through to models. And so then we cut some of the panels on our CNC router. So a lot of the detailing went in here, and this actually took quite a long time for us to actually generate something quite complex like this. So in the space of a 4-day workshop, the sort of hacking stuff together quite quickly was a very effective way to design and develop. But actually using these CAD-CAM systems did actually slow us down quite a lot. So we also introduced some new software we've developed for robotics called Godzilla, which is another animal-themed name. But the Bartlett have just got a couple of robots, and so we were helping them set them up and actually demonstrate how you can use robots to fold sheet materials. And this is us building the structure. So it got pretty messy. The way this kind of worked was that we had these two surfaces, and the only way we knew we had kind of finished building this thing was when these intersections lined up. So that was our big challenge. We started with having a lot of difficulty bending the metal at the sort of scale we were using into the right curvature, but with a few hundred zip ties, we were able to actually pull that together at these intersections, which defined the correct geometry. So we really didn't think it would actually go together, but the more we pulled the zip ties, the closer it got into the point where it kind of finally went together. And this is it suspended from the ceiling in the final installation in the exhibition. So hand over to Dan.
Okay, so a lot of my research over the last few years has been about using physics and physics engines in the design process. And one level that I've explored a bit for a while has been actually simulating material properties, but what I've been focusing more on recently is using physical dynamics to optimize for geometric constraints. So here, this is some simulation of the folding system that we started working with for the design. And so here's our mechanical system. Relatively straightforward to simulate a few of these elements, but it's about the way that the multiple geometric constraints start interacting when we have a lot more of them together. So what the physical simulation allows us to do, and this is the design for the final thing that we built, is it lets us take these geometric constraints and see what shapes we can make with them. And we've talked a little bit the other day about Sketchpad, and this has always been a big inspiration to me. There was this iterative constraint solving system within Sketchpad, and this is something, it seems quite strange to see something so old with this kind of system in, but and certainly now the way we model orthogonal constraints and make a simple 2D sketch, we wouldn't do it using this kind of iterative system. But I think there is a need to go back to those kind of iterative systems when we have more complex dependencies. So it's fine, if it's a simple system, we can do it with a very clear order of evaluation in our parametric model. And these directed acyclic graphs, where there's a clear order of evaluation and dependency, makes sense. But in these kind of systems, the only way we can really find the shape is by having everything depending on everything else and adjusting to find its form. So I'll hand over to Jeroen.
So just to finish off with some images, these are some images of some tools which we put together, which allow to link the analysis in real time with the form finding process in Kangaroo and other means. So that we're really developing tools which are sort of interactive and give us an immediate feedback, allow us to take decisions, design decisions, and which relate to the physics of the material and how this performs in a structure, both from a structural point of view, but also you see here a quick simulation from an environmental point of view, from a lighting point of view. And this is deep in the sort of workshop, folding and making plates. The realization of the sort of weakness of the material, you know, was quite interesting, and the comparison with the simulation was eye-opening. But I think it's the relationship, this kind of craftsmanship that comes out of workshops like this, and also the crafting of tools which are real-time tools, which really sort of help us understand more about materials and make these tools more reactive and more interactive. So Jeroen, do you want to talk about a bit about some of these images?
Yeah, so this is basically a walkthrough through the 4 days workshop. We started with small individual projects, and that merged slightly into two groups. One of the projects that Greg already showed with the curved aluminum folding. This one looks much more to the origami kind of structures where a surface with components folds together, and then with these actuators actually has this adaptive state. So the struts in between, you see them here with the, we showed them earlier, basically composed out of those strips of sprung metal, of tape measures, taped together. And it's a quite nice space underneath to lie there. So it's finalizing the completion, where this whole system forms a shell standing in itself. And you saw a couple of tools, how we connected them all with the digital world, the fabrication. And I think, do we have anything to add?
I think that's it.
That's it, so thank you very much.